Thank you, Ashley. Welcome everyone to today's presentation. As Ashley mentioned, my name is Kindred Cooper. I am a solutions engineer with Hegerman & Company, and joining us to run the Q&A in the background is Keith Dorn. He's also a solutions engineer with Hegerman & Company. And simulation is actually one of the specialties for myself and Keith. Today we're going to be going through how to design better using Nastran In-CAD. A little bit of housekeeping before we get going. I want to make sure that everyone can hear me. There is a meeting window. We're also going to be using that for the Q&A portion of the presentation, but obviously if you have any issues hearing me or any audio difficulties, that's where this slide comes in to help everyone. All right, so let's get right into it. So with Autodesk Nastran, what is it? There's still a big question out there with what exactly do we get with this product? And it is a purpose-built FEA tool that is built inside of Inventor. You get the benefits of your CAD product being right there at your fingertips instead of having to leave Inventor, go into analysis, come back to Inventor, and back and forth. You're staying inside the same program window. It is powered by Autodesk Nastran, and it's got a very broad spectrum of what it can simulate. Not going to go through every single one of these, but just to hit some of the highlights. Nastran is purpose-built for linear static analysis, buckling, modal analysis. You've got linear steady-state heat transfer. You've got composite materials you can work with. Obviously, assemblies with contacts. Thermal stresses can be played into here. You've got nonlinear statics. You've got nonlinear transient heat transfers, random response, frequency response, and what a lot of people ask for is drop testing or impact analysis. That's also one of them. But as you see, there's a wide range of the different types of tests it can run. And again, all of this stays inside of Inventor. What we're going to look at specifically today are the two most common types of analysis tests that are ran. That is a linear and a nonlinear analysis. Now, various degrees of what type of nonlinear analysis might be ran, whether it's a static or if it's a dynamic analysis or if it's some kind of temperature-related analysis. But we're going to look at linear and nonlinear static analysis for today's presentation, just kind of a preview of what's there. And you get the ability to apply a static load, which means the load is applied slowly. It's not a sudden impact load. And that's where the linear portion comes in with your materials and the loading application. That's probably the most common type of FEA that's ran across the board. Is just a linear static analysis. For a nonlinear analysis, you get more detail of what's going on. A lot of different things you can get from the results. You can see how contact between parts actually pushes stresses into other components and how the material itself might behave under certain conditions. You get to work with plastic-based materials, composite-based materials, and you're also looking at the situation where a large deformation is occurring. So it's difficult to say any kind of deformation above X amount is classified as a large deformation. You can't really plug a value on it. It's all dependent upon the situation and what you're doing. If you look at the cross-section of a I-beam, for example, depending on the size of that I-beam, if it's deflecting a fraction of an inch, that may not be a very large deflection. If it's deflecting multiple inches, okay, yeah, we're getting into a nonlinear analysis type that would need to be ran. But it also goes down to material thickness itself. If you're working with sheet metal components, for example, you get a lot of nonlinear behavior in a sheet metal component just because of the cross-sectional wall thickness of that component. The other types of analysis, as we saw, you've got dynamic response, which is basically time and frequency related, steady state and transient heat transfer analysis. Again, impact analysis comes in. Buckling, composites, fatigue, so wear out type of analysis, vibration. If you break all of these down, you've got a basic workflow that an FEA process goes through. First, you start out, you've got your geometry. The next thing you're going to do is assign your material. Now, this is where the FEA packages come into play, because you can assign a material in Inventor, and that gives you quite a bit of information. It allows you to calculate mass, it allows you to calculate center of gravity, that kind of thing. In the FEA world, you're going beyond just those limited factors. You're getting into Young's modulus, Poisson's ratio, to define the material characteristics and how this material is going to behave. So those pieces of information are crucial. I say that because if you've got your own custom material that is not part of the built-in libraries, you're going to have to get those pieces of information plugged in order for the analysis to function as it should. Once you've assigned your materials, then you can create a mesh. That's probably one of the most time tasking events of any FEA package. What you'll see with Nastran is it's incredibly fast. Once you've got your mesh, you can apply your loading and constraint conditions, maybe do some mesh refinement in there, then run your analysis and look at the results. With all of this, the goal is to validate what you expect or what you are witnessing happen in the field. And any changes that need to take place, it's much cheaper and faster to make those changes and test that theory here in the CAD product than it is to make a prototype out in the shop or out in the field and test it under those conditions. It starts to get very expensive once you walk out that door into the outside world. Our goal in here is to run design iterations to refine that design and zero in on that target performance that we want. What Nastran does with your model is it breaks it down into finite elements. So that's where the term FEA comes from. It's finite element analysis, breaks down your model into a series of simple shapes that it then can calculate and run the math against. For a solid model, you're most commonly looking at some form of a tetrahedron. If you look at something like a surface model, Nastran identifies that as a shell element. So we're not limited to just working with solids. We can also work with those surface models or shell elements. Breaks those down into triangles or quadrilaterals. And if you're looking at something like a frame structure, be it a machine frame or even a building frame structure, you can simplify it to break it down into line elements, which are then interpreted as beam or rod and connector points. And the goal of all this is to get accurate results. So when you're looking at something like a solid model, the amount of tetrahedrons you have is going to determine how accurate those results are. If it's too few, then you may not be getting enough information. If it's too many, you could be getting some stress risers that you may not even encounter. The benefit of using a shell element is it is a simplified representation of your model. So shell elements are used heavily on sheet metal type designs because you can make some assumptions and you work with a midplane. That midplane will reflect the inner and outer face conditions of that sheet metal shape. Then of course with the line elements, simplified structural analysis, if you're building a 20-story building, you're probably not too concerned with how the flanges might deflect under a certain amount of stress. You're more worried about the overall of the I-beam. So when you're working with something that large, like a 20-story building, simplifying it to a beam or a rod type element with connector points, you get the results faster. When you're talking about something like nonlinear materials, there's a whole wide world out there of what qualifies as a nonlinear material. If you look at the basics of it, every material on the planet is linear and nonlinear at some degree of their plot. So you could look at a material like steel. For the majority of the range, steel is a linear material. Then you get into a small window where it becomes nonlinear. Same thing goes for plastic. There's a very finite window where plastic behaves like a linear material. Then all of a sudden it explodes into a nonlinear graph. So depending on the material you're working with, you've got different options of what material type and the behavior of that material. Nastran can adjust for all of those. So one question we get a lot is, why do I need to use Nastran versus what Inventor already has built in inside of Inventor Pro? Well, there are limitations in Inventor Pro, one of which is it's linear only. It cannot work with any type of nonlinear materials or nonlinear calculations. Also, it's static only. That's the limitations for Inventor Pro. They are different analysis engines, and through our own testing, we have found that the Inventor Pro, the Plazotech engine, and the Nastran engine, they give you the same results when you're running the same type of test. So if you run a linear in one and a linear in the other, you're getting the same end results. So you've got repeatability across the two packages, but Inventor Pro has those limitations to only work with linear and static loading conditions only. The other thing that comes into play is, if you're working with a nonlinear material, do you have to run a nonlinear analysis? Well, no, not necessarily. You could run it as a linear analysis to kind of run a sanity check. Make sure you've got your constraints properly set up, make sure your loading conditions are accurate, make sure it's behaving the way you expect it to. I wouldn't necessarily trust the end result numbers because you would be working with a nonlinear material or a nonlinear situation such as a large deformation, but at least it's a very quick sanity check that, hey, it's moving the way it should, it's fixed the way it should, it's behaving the way it should. I just can't trust those amounts until I change to a nonlinear analysis. So with that in mind, let's jump right into it. And this is the process flow we're going to go through. We've already got the geometry, so we're going to jump into Inventor and look at the actual material that we're going to be working with. So as you see, if I go back to basic Inventor, your interface, your modeling interface, your browser tree, everything is there. If you look on the environments window, this is where Nastran comes into play. So when I launch the Nastran sub-environment, you'll notice I never leave Inventor. Now granted, the ribbon system changes, but I never leave the Inventor interface. The way the interface is laid out, much like a lot of the other sub-interface environments inside of Inventor, it's kind of like reading a book. You go from the left and move to the right, and that's basically what you're doing. You're walking through your different analysis types. You're coming and assigning materials, building idealizations, maybe building some connectors, then working on some constraints, applying some loads, looking at any possible contacts, generating a mesh, refining a mesh, running the results, and running the simulation and viewing the results. So that's why I say it's kind of like a book, left to right. So starting out, every analysis in here, when you first go into Nastran, defaults to a linear static. Now I can change that analysis type to any one of the other sub-analysis types that I have. Bring that window over. From linear static to a normal modes to a buckling to nonlinear static, all of your different analysis types are here. Now as you change through these, you get different options for the analysis. So looking at a linear static, I can look at what kind of nodal output controls I might have or what kind of output sets I want to watch. If I look at my options, when you're working in an assembly, you can set a default contact type and what type of tolerance distance you may be working with. If I change to a nonlinear static, I get a few additional options on the output controls and a few additional options on the options tab. So based on whatever type of analysis you're running, your various optional controls here will change and adjust automatically. You can also override your units if you want to change from pulling from the CAD model. Maybe you want to use standard units or go back to metric. Right now I'll just run with the defaults, running with a linear static. So step one in here, when you've got your material, or when you've got your model, you want to set up what kind of material you want to work with. And Nastran will pull in whatever material is assigned in Inventor. That may be what you're going to run the analysis with, maybe not. You can change that with the idealizations. Idealizations allow you to set up different sub-object types. So what we're working with is a set of solid elements. It's a solid model, so we're going to work with solid elements. If we're working with something like sheet metal, that's where we would plug in and say, well, we're going to work with a shell element and we're going to control its thickness. Or if we're working with a frame structure, we're going to work with a line element and various controls for that if it's based on a structural member or a cross-section profile. You can work in a mixed case, meaning you could have an assembly that has some solid elements and some shell elements and some line elements. So you can mix and match these as you see fit. What it's got right now for this particular idealization, it's got it set up as a mild steel. I'm just going to change that to an aluminum material. Now, you can plug in for your own custom materials if you want, and this is what I was talking about earlier. You're going to have the values for the Young's modulus, for the Poisson's ratio, for the stress, things like that. You're going to have to plug those values in here for your custom material in order to get accurate results out of the software. If you use the default libraries, the Inventor library isn't bad. It's got quite a bit of material in here, and all of the properties come in with it. The Autodesk material library is far more extensive, a lot more options to plug in and look at. So let's say, for example, I wanted to run with aluminum 1100. All of those values are plugged in for me from the material library. So I'm going to apply that, just change my mesh color of what I want it to look like. You'll see that is a solid element taking on that aluminum material. The next stage is to apply any kind of constraints and loads that you may need. So for something like this, with this particular mechanism, I'm going to apply a constraint. It's going to be a fixed type of constraint, but you'll notice here we can apply a fixed, we can apply no translation or no rotation, and you get control over the translations of X, Y, and Z and the rotations around X, Y, and Z for that selected entity. You can select faces, edges, points, optional controls for what you may want to colorize these constraint glyphs so that you can see in the model, here's where it's being constrained or here's where it's being loaded. Again, all of this is kind of optional. I'm going to set this up to be a fixed condition. That's going to be the only constraint that I apply. The next items I'm going to apply are two different load values. So when I apply a load to this, you've got different types of loading conditions, from a force to a moment, pressure, enforced motion, temperature loading, radiation loading. For this, it's going to be a force load. And what I'm actually going to do is I'm going to put 1,000 newtons across the top two drilled holes. Now, when I apply this, I'm going to apply it in the Y direction. There's my 1,000 newtons. And then there's a very important checkbox in here that is often missed. If my total load condition is 1,000 newtons, I do have a total force checkbox. Now, this is the advantage that Nastran gives you over a lot of the other analysis packages. If I just leave it as this, then each one of these faces are going to get 1,000 newtons loaded against them. That does not reflect what's happening in real life. So that would give me a poorly exaggerated result. So if I choose total force, it's going to split that 1,000 newtons. And again, optional controls for things like your glyphs to define your constraints and your load situation. So I'll apply 1,000 newtons to that set of faces, and then I'm going to apply another loading situation to the other two drilled holes on the bottom of the rung. These are going to be in the X direction, and again, it's going to be a negative direction because it's going negative X. and I'll apply it at 680 newtons, and again, optional controls for the glyphs. As you can see, applying the constraints and applying the loads is very simple and very fast. The next step, when we're looking at a piece part, there are no contacts that come into a piece part situation. The next step may be to look and say, okay, do we need a constraint, or do we need to build in some kind of mechanism that reflects what's going on? Looking at this particular lever arm, there's probably a shaft or some kind of bolted connection that's holding the center pivot point right here. We do have the option to build in connectors into our model geometry. This is an advantage if we have something like a bolt connection, for example, that's going to be holding this on that center pivot. You don't want to model a bolt and a nut and a washer, or if you do, you don't want to include them in the analysis. They tend to complicate the math and can skew the results sometimes. And we can look up material properties and behaviors of bolts and nuts and see how they're going to perform under stress loads. So we don't need to plug that into the analysis. We need to look at everything else. Using a connector utility, it allows you to build up a bolted connection without having the geometry in the way. It'll give you a small preview of a bolted connection, but there won't be any geometry to run math against. So it saves you time on your analysis, keeps everything simple, and it applies that type of constraint, whether it be a bolt type connection, a rod, or a cable, or something to that effect. So once you have your constraints and you have your loads built, then it's time to actually look at the mesh. This is where you really need to take time and focus, and with other packages, this is where a lot of time can be eaten by you waiting on the mesh. You see how fast I got that mesh. Nastran has probably one of the fastest mesh engines I've ever run across. There's only one faster that I've seen, and that's Autodesk Simulation CFD. It is a super fast mesh engine. But Nastran is very fast as well. We can look at the mesh, get a good preview very quickly. The controls are incredibly easy to navigate. It gives you a calculated default mesh based on model geometry. You can tweak that to make it a more coarse mesh, or tweak it to make a more fine mesh, whether you use the slider or if you just plug in. Say, well, let's make everything 5mm. So regenerate my mesh, takes a couple of seconds. You got a brand new mesh to work with. One thing you may note is if you're looking around the filleted edges, you're not seeing a mesh, and that could throw some people. They may think, okay, well, why is it avoiding that area, or why am I not getting a mesh in that area? Now, with other mesh packages, we've seen issues where it doesn't like going around curved edges. For Nastran, it's not a big deal. You go into your mesh settings, and you can actually turn on mid-side nodes, and what it will do is on any rounded face, when I regenerate this mesh, you'll actually see a mesh line divide those filleted corners. So it allows you to see, here's how that mesh is getting calculated around that curve. That's important, because when you're looking at the mesh of a model, you want to make sure, one, that the distribution is nice and uniform. You don't get any crazy sudden changes in your mesh pattern for no obvious reason. You know, you start going around drilled holes, the mesh pattern is going to change orientation. It may even change size a little bit. You go into a smaller face, such as the chamfered faces of the drilled holes, it's going to change size, it's going to change orientation. Those make sense. Looking at a flat face like this, if you suddenly see a change in the mesh, there's a topology problem with your model. Now, we could be working with a downloaded model. Could be a downloaded pillow block that's crucial to our design, or downloaded bracket. That's typically where we'll see issues like that, not necessarily with something that's natively created in Inventor. So looking at this particular mesh, looks good, looks clean, looks uniform all the way around. The next obvious step is to just run the results. This is another area where Nastran passes all the competition. It's how fast we get those results. You'll see very quickly the analysis engine kicks in, starts running, and it just takes a few seconds to get a good linear static result. It'll prompt me and say the solution has completed. and immediately takes me back and looks at the results. Very, very fast result engine. So looking at the stresses we've got in here, right now we're looking at the von Mises stresses. We're looking at the megapascals. If you communicate in PSI, you can change that by all means. You've got your von Mises, you've got your displacement. Now, this is just out of the tree. You've got the four most popular ones to look at. If you look at the top of the analysis weather map chart, you can change just looking at stress. You can look at solid normal X, normal Y and Z, shear stresses, principal stresses, min, max, mean, equivalent. You've got all of that there. If we look at something like displacement, see how far this thing's actually bending. Change it over to inches. It's bending about 32nd of an inch. Not a lot. Granted, the preview is going to be exaggerated, but the actual amount is not bending much. At this point, we're only looking at total displacement, but we can also break it down to see what's the displacement along the X, Y, or Z axis and look at that result independently. Safety factors are also automatically displayed as one of the four main ones, and looking at the actual deformed model. So what if we make a change? That's where the big money comes into play. Changes are expensive, especially out in the shop, but at the engineer's workstation, not so much. So if we need to make a change of this, let's just get out of Nastran, come back to the main model, and I'm going to shorten this bracket a little bit. I'm going to take 10 millimeters off the overall length, the top and bottom legs. Finish my sketch. Of course, my solid model updates. Let's go back into Nastran. With other analysis packages, we would have to start over. We would have to go back and redo our constraints, redo our loads, all of that. With Nastran, no. All of that is retained. It remembers because those faces and those edges, they're still the same. They still exist. They didn't disappear. Now, granted, if you make a change and it blows away a face or an edge, you probably have to reestablish something because it lost association with that face or edge. But for this particular example, everything stays. Granted, the mesh is out of date. That's an easy fix. Let's just regenerate. Regenerates based on the new geometry. And let's rerun the results. That's how fast we can get results and not liking those results. So let's make a change. Go back, make a change, get new results, and interpret the difference. Which one do we want to run with? Which one is giving us the better performance? Is the longer bracket the better way to go, or is the shorter bracket the better way to go? You know, which one has the least amount of stress depending on that situation? So that's the benefit of having something like Nastran In-CAD is you're never leaving Inventor, and you've got very quick responses on anything you do, be it applying loads constraints, be it generating a mesh, making a change, regenerating a mesh, and getting a results. Everything functions incredibly fast in here. This is working with a piece part. What about assemblies? Well, let's go open up an assembly. Look at something similar, a little bit more on this particular type of mechanism. We still got the same cast lever, but now we've got the two pins in here that are going to be controlling it. In this particular example, we're only looking at half the model. So we could actually set up some symmetry in here, run the analysis on half of the design, and save some time. If it's a symmetrical design and symmetrical loading conditions, then of course the stresses are going to be symmetrical as well. So when I come into Nastran for this one, same thing still applies. We're going to look at assigning a material. You also have the option to have your own custom material database that you can pull in. You're not stuck with just using the Autodesk library or the Inventor library. For this particular one, I'll keep the mild steel assignment for the main bracket. Last time we worked with aluminum, but I'm going to make it steel for this one. And for the pins, I'm going to assign them an alloy steel. Actually, maybe I will go back and change that main bracket, make that an aluminum versus the alloy steel. And I'm going to associate it with these two particular pins right there. They are solid elements. And like I said, I will go back and change this. Let's play around with this a little bit, make it aluminum, and see what kind of results we actually get. So stick with the aluminum 1100. Now I need to look at applying my constraint and loading conditions. I'm going to put a fixed constraint on the outside of the pins. So what that's actually going to do in this situation, it's going to lock them down to where they cannot move in X, Y, or Z, and they cannot rotate around X, Y, or Z. So that's going to invoke that fixed constraint through that model and into that bracket. The other thing I'm going to apply is symmetry. So we need to lock down what I'm going to call the middle face or the cutting plane of all of this. And when I apply that symmetry, it's actually going to be symmetry along the x-axis or perpendicular to the x-axis. So I'm going to choose X symmetry, and by doing that, the translation of Y and Z and the rotation around X are freed up. The only ones that get locked down are the translation in X and the rotation around Y or Z. So I'm actually going to lock down these three faces for that X-axis symmetry. Okay. Lastly, I'm going to look at applying the load condition. Now in the previous one, we applied 1,000 pounds total force to the top. For this particular example, it's only going to be 500, I said pounds, it's going to be 500 newtons in the negative Z direction. Run my mesh. Let's take a look at it. Now I know from the previous result when we ran it as a part, as a single part, looking at that weather map of where the stresses were, I know that the internal surfaces here, the internal corners and radiuses, had the most stress. So I may want to adjust the mesh a little bit just for these areas. And I can do that by invoking a local mesh control. Now with the mesh control, you can control the vertex of the mesh or the face, the element size, based on the face selection. So what I'm actually going to do is I'm going to select these three faces right there, and I'm going to cut the mesh over, I'm going to cut it more than half. I'm going to go down to a 2 millimeter mesh just on those three faces. Go ahead and click OK. Now I will have to regenerate the mesh. I'm going to change my settings real quick before I do that. Go ahead and look at my mid-side projections and regenerate that mesh. Now what you're going to see is the mesh is going to change slightly. We did get refinement on those faces. The mesh elements of those faces got smaller, and in any of the connecting faces, it evenly distributes that mesh size change through those faces. So it did refine them. We're getting a much smaller mesh in here, and that's a benefit. That can help us focus in on an area that might be having some stress. For that matter, the stress could move because we're working with a finer mesh, we're working with more detail. It could relocate the stress area or the center of the stress. So now I can just run my analysis. And again, we're working in an assembly. They will typically take longer than a piece part. You've got more things coming into play here. And actually, yep, I'm glad that did that, because we missed one step on this. Working in an assembly, I didn't look at any contacts. So the software is giving you a little bit of a sanity check in of itself. It can't run the analysis because you've got some parts in here that interconnect and they're moving too much. So I'm going to come back and I'm going to run an automatic contact detector. So this goes back to my analysis settings, and it looks at how close the faces of different components are to each other, and it will apply a default contact, in this case a bonded contact. It'll apply that to those faces. Look over in the tree, you can see the surface contacts that it applied. It's got a bonded contact between the pin and the lever, the large pin and the small pin and the lever. And you can change these. I can come in and change it to a separation contact or a sliding no separation contact, various different types of contact depending on your situation. Bonded, the best cousin you could think of is like a welded type contact or other type of fixed contact condition. A bolted connection could create a bonded contact, for example, to where that movement is restricted. I'm going to go with a separation on both of these, and I'm going to put in a max activation distance. So what that does is it says anything outside or above 2 millimeters, it's not going to run any math. So as these pieces start to move, if they are outside of 2 millimeters, let's say they have a gap between their face, between their two faces, let's say a gap of 3.5 millimeters, there's no math ran on them at 3.5 millimeters. As the pieces start to move under loading and under constraint situation as it goes through the analysis, when those two faces get within 2 millimeters, that's when the math kicks in. And that's really the only time I care about it, is when it kicks in at that 2 millimeter mark. So I'll change that on both of these to a separation contact. Got my mesh, got my loading, got my constraints, everything looks good. Now it should be good to run that analysis. And again, you're running it on an assembly. They typically take a little longer than a single piece part. And you'll see how fast this assembly analysis does. We're still running a linear static analysis, and it's already done. So I can just jump over here, take a look at my results. There's my von Mises megapascals. Let's look at PSI, see how it changed, see how much forces or stress is being encountered. And right there, the stress moved a little bit more towards the outside and not so much on the inside. So another thing I may want to do is I may want to come back and do more mesh refinement on some of these outside faces to make sure it's not going to move again, or make sure that the amount is correct. The benefit of having Nastran as your analysis engine is you can run different scenarios, and that's where the subcases come in. We have one analysis, linear static. I could make another subcase. We'll just say a brand new subcase, and for this one I want to reuse those two constraints from the previous subcase. But I'm going to apply a different loading condition. So on this one, I'm going to come in and I'm going to apply a load to the same area, but this time it's going to be 750 newtons instead of just 500. You'll notice you can choose which subcase this new loading condition applies to. So what you're actually doing is, under one linear static analysis, you are creating different loading scenarios and constraint scenarios. And the sky's the limit. However many you want to plug in here, you can plug in. The takeaway is the more that you have, the longer it's going to take. When you run the analysis, it's running for all of your subcases during that analysis run. So you can look at your results on a 500 Newton load and then snap down and look at your results on a 750 Newton load. And you can compare the differences. All of that is with your linear static. What about nonlinear? This is where it can get very extreme on making sure everything is right. Material specs are a must. You have to make sure you're working with the right material. You have to make sure that you have the right values for your material. When we get support calls that an analysis is not showing the proper results, over half the time the problem is with a material spec. Either the material that they are using from the library does not match what's out in the shop, or vice versa. There could be something off. From my own past experience, I know that we poured ductile iron at a different density than what all of your material libraries called out. We also had slightly different Young's modulus calculations than what all the libraries called out. So you've got to get those right. Nonlinear materials, it's a huge ball game in that area. When you change to a nonlinear static analysis, you've got some additional options, and this is the benefit of running a nonlinear test, is you can get snapshots in time. So we've moved from a linear static into a nonlinear static. A couple of options have turned on here, a couple of options in your options tab if we're looking at large displacement and things like that. Now I've gone ahead to save some time. I've applied some loads, I've applied some constraints, and I've applied some material. So we've got alloy steel on the two pins. That's the white colored mesh. Then we've got ABS plastic on the purple color mesh. Now, when you're specifying a material, you can override any of these values in here. Again, these just are the defaults that come from the library. If you've got a material sheet that says different, plug in those numbers here. When you're working with a nonlinear test, you also have the option to come in and specify what material type we're dealing with. Are we dealing with a nonlinear elastic? Are we dealing with an elastoplastic or bilinear material, or straight plastic material? I say straight plastic, it's not that simple, because you've got other things such as the hardening rule that plays in here, what kind of yield criteria you might want to look at, and you can even override to say at 50% of strain, we hit the yield of 43 megapascals. So how's that going to look on the analysis? When you have an analysis for nonlinear, in the subcase, and this is going to happen for each subcase that you have. In this particular example, we just have one. If I go into the nonlinear setup, I can plug in how many increments I want to look at. So what the nonlinear test is going to do is it's going to break your loading condition up into however many increments. So if I did 10 increments, for example, if I'm applying 100 pounds for my load, then the first test is going to be done with 10 pounds. That's your first of 10 increments. Second test, it's going to be done with 20 pounds, then 30, and so on and so forth. So that's really what the increment is doing. One, it's breaking up your loading condition. Two, you can actually tell Nastran, I want to grab these intermittent snapshots in time. I want to look at those values. So when it plugs in 30% of my load, or 40% of my load, or 45, or however many increments you're running into here, when it plugs that in, I want to be able to go back and see that in the results. So I want to grab that piece of information. That's the big benefit of running nonlinear, whether it's with materials or deformation. This is a big benefit to where you can actually dive in and see exactly when does the material exceed that stress amount. And that's what we're going to be able to do. The downside with any kind of nonlinear analysis you run, and I don't care who you run it with, they're going to take time. You've got a lot of math going on here, a lot of things happening in the background. Nastran is no exception. It's still very fast, but it's still going to take time. This particular test, when I ran it previously, it was just over 10 minutes. But what happens is you're able to see, as it runs through these iterations, you're able to see those tests, those different iterations and different increments get calculated on. So you're kind of getting a progress report and kind of seeing live results at the same time. I'm not going to drag us through that. I'm just going to stop this analysis, and then I'll load results from a previous run. So there's another benefit of Nastran is you can have multiple tests and multiple results that you've ran and saved out to your hard drive somewhere, and at any time you can load those up. So I can come back and load up that previous test. It loads up all of that data, loads up the constraints, the loads, the materials, and the results that were generated. So when I look at my results, I'm just going to display my solid von Mises stress. And what I'm looking at right now, I'm looking at megapascals, and I'm looking at increment load. The load amount is 5% of what I applied. I don't remember what the amount was. I think it was like 35 newtons or something like that. So I'm looking at 5%. That's what the load equals refers to. I can jump through time and say, okay, well, let's just go ahead and look at 100% loading. Let's see what that shows us. And when I do that, right there, my max stress, it exceeds the 43 megapascal yield that I plugged into the chart. So at 100%, this is going to fail. It's not going to withstand the stresses. But what nonlinear does for you, because we're grabbing those increments, we can dial back in time and see not exactly when, but get a better idea of when it will actually exceed that yield. So there's 100%. What does 50% look like? 43 is our max. Okay, we're at 32 at a 50% load. Let's dial it up a little bit. Let's jump up to 75%. We go from 32 to 48. So even at 3/4 of our loading, 75% of our loading, we've exceeded our yield. We're at 48 megapascals. So somewhere between 50 and 75% is when it's going to exceed that. Well, we can dial it in. We've got 5% increment breakdown here. So let's look at 65%. 65 shows us 42.6. I'm going to say between 65 and 70% is where this thing is going to exceed yield. So if I jump up to 70%, right there it is. So somewhere between 65 and 70% for my ball game, that's close enough. I know it's somewhere in that area. So that's the benefit of running with a nonlinear analysis, is you're able to grab those types of increments or snapshots in time, if you will, as it applies that load. And that's for any of the nonlinear level analyses that Nastran will run. You don't get that on a linear output, just only on the nonlinear. But as you see, it was all incredibly fast. And again, if I wanted to go back and make changes, bounce back into the main Inventor interface, make a change, come back in here, everything is retained. I just have to update my mesh and rerun my results. So as you see, we followed that timeline pretty well. We had our geometry, we worked with our materials, worked on the mesh, even refined the mesh a little bit, had our loads and constraints, and looked at our results. There are other aspects of simulation that Nastran can help with. We've got some of the thermal induced stresses, some of the transient type stresses, but there are some other areas that it's not really Nastran's forte. That's where these others come in. Nastran falls into the mechanical category here on the left, but we also have Autodesk Simulation CFD, and that's for your computational fluid dynamics, airflow, fluid flow, and heat transfer. Nastran does do some heat-related stress analysis, but not to the degree that CFD does. So there's a different program plugged in for that. You also have something for plastic mold filling. That's your mold flow application. If you work with injection molded plastics and patterns and things of that nature, that's the product you need to look at for how your mold is being filled, how your temperature is dissipating as it cools, looking at your cooling mechanisms, your cooling tubes and things like that. Working with composites, that goes back to Nastran to work with composite materials. And building structure, we have on the architectural side of things, there are analysis tools to work specifically with building structure to get loading analysis, temperature analysis, things like that. Some of the other areas that Hagerman can help you with document management for Autodesk Vault or Adept or Meridian. We have experience in all of those applications. Looking at Vault specifically, we've successfully done over 1,100. I think it's actually much higher than that now. Implementations with customers that are still in use. They're using it daily for the management of their documents, to control lifecycle states and revision control and check in and check out and track changes and things of that nature. Simulation services, we bring over 30 years of experience for simulation. We have our own internal simulation team that can work with you for specific projects. Not talking training, we're talking actual hands-on. You bring a problem, you want the results. That's what that team is there for, to deliver those end results to you. I think at this time we will open it up for any lingering questions that might be hanging on. Keith, is there anything out there in the Q&A window that you want to address?
Yeah, there's two of them that are still kind of sitting out. The first one is, can you walk through some of the transient response setup requirements? So basically just the dialog box for a nonlinear transient.
For our time constraints on this, no, it wouldn't be very practical. What you can do, if you want to contact your Hagerman sales rep, that would be just a quick little web demo that we could walk you through. When you get into things like that, it's best to address exactly what's going on and address the situation instead of generalizing it. That's how we
Sure.
prefer to approach that.
And then one of the things that I was not, one of the things that I don't know the exact answer on is, can Nastran do stress linearization, or whether it be membrane or bending? And if so, what standard does it use? And I don't know the answer of that one offhand.
I don't either. I think it's going to take a little bit of digging for us to find that information out.
Another question that just came in that is a very easy answer. Do we offer training on the product? And that is absolutely the case. We offer training on pretty much all of the simulation tool set that you just saw Kendra discuss, whether it be the FEA within Inventor Pro, which obviously we don't recommend anymore, the Nastran, CFD, definitely we can train you on those.
The only one that I'm aware of that Hagerman does not offer training on is mold flow. For that one, I believe Autodesk requires everybody to go directly to them.
Yeah, and we've actually had the mold flow training in our office before, and the trainer for that is a material engineer with like 25 years of experience. She is very good at not only showing how the software works, but also explaining the material sciences behind what it's doing and how it's solving it. So she does a very good job with that.
Any other questions from anyone? Give you just another minute. If you do think of any questions after today's webinar, by all means, get in contact with your Hagerman sales rep. I believe Ashley can correct me if I'm wrong. I think there's a way to submit questions through our website.
Yes,
maybe through our YouTube channel.
There is, but you can also just reply to that confirmation or reminder email that you receive from GoToWebinar, and we can get those to the appropriate person to get your questions answered.
One good question just now popped in. How does the process work for you working with us on an FEA problem we need solved? I'm going to nutshell this as best as I can. Obviously, you come to us with the problem that needs to be addressed. We get our simulation consultants online with you. Once everything's agreed upon, quote and price and all that jazz, then they would work with you directly. It could be web-based, it could be on-site, however you want to approach it. But our simulation team would take that over to handle making sure you got the results that you were expecting. That's kind of just nutshelling it, because once you start talking about that, it could go branch off into a dozen different directions. You could try different iterations, different materials, and start expanding on it, and who knows how long that could take. So we kind of just toss the ball to them and let them address that directly when you meet with them to discuss what your expectation is out of that. Any other questions? All right, if you do, again, as Ashley mentioned, you can reply to the email to enter any questions. You can log some questions to our website. Contact your Hagerman sales rep is another way to submit the questions. At this time, I appreciate everyone joining us for today's webinar, and appreciate the questions and the feedback, and everyone have a great day.
Bye, everybody.